Okay, so we'll get started here. Our group wanted to do our project on non-Newtonian fluids, and what we hoped to achieve throughout this project was just to state some observations of characteristics of these fluids to try to determine how and why we are actually able to walk on non-Newtonian fluid. So basically, a non-Newtonian fluid is just a fluid that doesn't follow Newton's law of viscosity. Newton's law of viscosity, as I'm sure you remember, is just a fluid that behaves according to Newton's law with a viscosity that is independent of the stress is said to be Newtonian. So we're going to be taking a look at non-Newtonian fluids and how they deviate from this law a little bit so that we can try to determine how and why we can actually walk on these fluids, but we aren't able to walk on a Newtonian fluid, say like water. Now, the two observations we chose for this portion of walking over a non-Newtonian fluid would be a person standing still, and they will sink through the fluid, while a second person then will be able to walk or hop or even run across this fluid. The definition of viscosity is the measure of a fluid's ability to resist gradual deformation by force. Our hypothesis is that when the force was applied slow and steady, it allowed the fluid particles more time to disperse due to the decreasing viscosity, which would ultimately create a liquid-like surface, causing the person to fall. However, when the force was applied fast and sudden, it did not allow the particles time to disperse due to increasing viscosity, which would create a semi-solid surface temporarily. And this video kind of demonstrates that in action, as you see the fist try to punch the non-Newtonian fluid and it's not even able to break the surface. Next, we move into the analysis portion of our presentation, where we noticed that shear stress was the main characteristic that we needed to be looking into. In the equation, you can see that the shear stress is equal to the dynamic viscosity of the fluid, and it is multiplied by the velocity of the fluid along its boundary. So the two types of fluids that we really wanted to look into in our analysis portion were shear thinning fluids and shear thickening fluids, as these two directly relate to our initial question, why and how are we able to walk on non-Newtonian fluids. In a shear thinning fluid case, viscosity will decrease with an increase in shear stress, and the harder a fluid is sheared, then the less viscous it's going to become. Controversially, in the shear thickening case, viscosity will increase with an increase in shear stress, and the harder the fluid is sheared, the more viscous it will become. So ultimately, we can take a look back to our observations and our hypothesis at this point, and see that in our first case, with the person standing still on a non-Newtonian fluid, and they actually sink through the fluid, this is due to the decreasing viscosity of the fluid, which we can define now as a shear thinning fluid. Viscosity decreases with an increase in shear stress, causes the fluid to be less viscous. Controversially, in our second case, with the person that can walk, hop, run across the non-Newtonian fluid without sinking, we can look and define that now as a shear thickening fluid, where the viscosity is increasing with an increase in shear stress as well, and then the harder the fluid is sheared, the more viscous it becomes, which is ultimately what allows people to be able to walk on these non-Newtonian fluids. To take our analysis a little bit further, you can see through that equation tau is equal to mu times dv over dy, that the shear stress and viscosity have a directly correlated relationship. In the first example of the person standing still, the reason that the fluid is not able to hold the person is because dv dy, or the velocity here, is 0. So when you plug that into the equation, mu times 0 is 0. In the second example here, the person is running across this fluid instead of standing still. So dv dy, or the velocity, would be a non-zero number. And when plugging that into the equation, multiplying it by the viscosity, you would be able to see that tau will also be a non-zero number, which demonstrates that the fluid would be able to hold this person up. So to conclude here, we would like to answer our original question, which is why and how are we able to walk on non-Newtonian fluids. And ultimately, you can see this in our analysis under the shear thickening fluid. Viscosity increases with an increase in shear stress. The harder the fluid is sheared, the more viscous it's going to become. So to conclude an answer to our original question, we are able to walk on non-Newtonian fluids due to the shear thickening fluid, where the viscosity is going to be increased, which will allow us to walk across it as if it's one solid material. One of the other conclusions that we came to is that the more an object or body tries to exit the fluid, the harder it's going to be. The fluid's going to hold them back, is what we kind of saw in our second analysis slide.